Thanks, everyone. This talk is joint work with my PhD advisor, Itai, with Mark at Princeton, and with Yash at Columbia. Let me just parse the title for you a little bit. So this paper is about how much communication is needed to find a stable matching in a two-sided matching market. So this is an important problem because matching markets determine which firms we work for, which schools we go to, and whom we marry, all very important things in life. However, if a lot of communication is required, then the market might not be able to process things fast enough to reach a good outcome. And we will show that the key to achieving reducing communication overhead is this term, informative signaling. Let me state the motivation more precisely. So by good outcome in this paper, what we mean is stable matching, which is one in which no pair of agents will prefer to be matched to one another rather than their assigned partner. So this is desirable because matchings that are not stable may unravel upon itself as people start deviating from the matching. So this is a very important concept in the theory of two-sided matching. It is used for the empirical estimation of preferences from matching data, and it's also a central consideration in the design of matching markets. However, in recent years, there's been a series of work that show that in the worst case, finding a stable matching may require a lot of communication. In particular, Ilya's paper in 2007 shows that for any method of finding a stable matching, there exists some preferences such that agents on average need to communicate order n amount of information, where n is the number of agents. So for markets with many thousands of agents, this can be a very large communication overhead. And in fact, Yanai and others extended this result to allowing randomized algorithms and only asking the protocol to find a stable matching with high probability. So if so much communication is required to find a stable matching, do we really still think that stable matching is the right concept for large markets? So the point of this talk is that instead of worst-case preferences, we look at more natural preference distributions. And what we see is that in this case, it is indeed possible to find a stable matching with not so much communication, and agents don't need to learn their preferences over everyone. Also, the protocol we have will have good incentive properties, which means that it is agents would not want to deviate from the protocol. So there are two implications about this kind of work. The first implication is that this defends the plausibility of this solution concept of stable matching for large markets, which is important since there's so much literature based on this concept. The second implication is that the properties of this protocol give us some insights on how to reduce communication overhead in real markets, which I will comment on later. So now let me show you the model. So this will be a simple two-sided matching model with two deviations. One is that agents will need to learn their preferences. They don't know who they like a priori. And they also need to communicate that to the market. And we would also define the assumptions on preferences. So here's the matching model. There's a set I of workers and a set J of firms. People have preference distribution. So preferences are this ordinal rank order. So each worker has a favorite firm, second favorite firm, some set of firms they don't like, and likewise for firms. But the preference distribution may depend on this unknown state of the world omega. This is abstract for now. I'll make it more concrete later. So to learn their preferences, agents query a choice function, which specifies as input a set of potential partners and outputs the agent's favorite partner among this set. So who is my favorite firm among these people? And so this is the only way people have of learning their own preferences, which is a priori unknown to them. Also, we're going to keep track of communication. Formally, a communication protocol is a function that maps the history of communication to which agent should be the next one to communicate and how they should communicate. And for now, we will assume that every agent sees the entire history of the communication. So to account for costs in preference learning, we just count the number of these choice function queries. And for communication, we'll count the number of bits communicated per agent. So just as a warm-up, let's apply this framework to look at this classical Gale-Shapley deferred acceptance algorithm to find a stable matching. So just as a review, essentially, we find an unmatched worker, make that worker apply to her favorite firm that she hasn't applied to, and then workers will keep on will take the application if the firm doesn't have anyone, but if there's an incumbent, then the firm keeps the more preferred applicant and rejects the other one, who then later applies to their next match. It's the standard stable marriage Gale-Shapley matching. So this algorithm, if you do the accounting, has high preference learning and communication costs in the worst case, because each agent may need to go through a substantial fraction of their entire preference ordering. So that's per agent omega n choice function queries, and also around linear order number of bits sent or received per agent. And Ilya's result, as well as the other result by Yanai, shows that in the worst case, even if you allow the algorithm to fail with small probability, this is essentially the best you can do. So to get tractability, we will have some assumptions on the preferences. So the assumptions on the preferences are as follows. We make no restrictions on the preferences of the workers. However, for the firms, we assume that they're induced by this random utility model, which is a latent model. So the utility of firm J for worker I is equal to two terms. There's an observable public term, observable to the worker I and firm J in question, as well as an unobservable term that's distributed IID according to some firm-specific distribution that is actually unknown to everyone. So recall that even the firm itself needs to learn preferences using the choice function query and don't know the epsilons themselves. And we also make a technical assumption, which is that basically this private term is sufficiently large compared to the public term. And this is necessary to get past some of the previous impossibility results, because we have a very flexible model allowing these observable terms to be for each worker-firm pair. And precisely speaking, the assumptions are we need the tail of this distribution to be heavy enough, and we need the range of these public scores to be not so large. So that is the model. Let me just sketch out the results. So this is the main idea for the protocol. So the idea is that we want to discourage these bad fits. So basically, in the Gale-Shapley deferred acceptance, there's a lot of wasted communication because people who have no chance apply, and then they waste their own time, but they also waste the time of the firms who has to screen so many people. So the key idea is to discourage these people who have no chance anyway. And we call this model for firm preferences. Someone only has a chance, has a high utility, if either they have a high public score or they have a high private score. So the protocol we'll propose will have two rounds. So in the first round, firms signal workers who have a high private score. As well, firms throughout the protocol will keep track of this qualification requirement Z. You can think of this as some guidelines, like if you want to apply to me, you should have this kind of degree, this many years of education, etc. Otherwise, don't reach out unless I send a preference signal to you. And then we'll do the worker proposing deferred acceptance with workers applying only to firms that they either have a high epsilon because they got a signal, or their public score exceeds this qualification requirement. So here's the details of the protocol. So initially, the qualification requirement is set to this low number. And then in order to implement the firm signaling, because firms don't know their epsilons, the way we do it is that firms partition people into bins according to the public score and just signal their top order square root n workers from each bin. And then, as I mentioned, we have worker proposing DA with workers only applying to firms in which they have a chance, either a high enough public score or they receive the signal from the firm in step 1. And finally, the key to making this work is this updating of the qualification requirement. So we want to increase this qualification requirement fast enough so that we discourage these bad fits. However, we don't want to increase it too high so that there are people who would otherwise be qualified who get mistakenly turned down. And the magic threshold is some rate like this that makes the proof work. And this uses the fact that these epsilon IJs are IID. So if I see so many applicants who have a high enough public score, I probably would like one of them. So that's the main idea. So this protocol that I just showed always finds a stable matching with high probability in a separable market. As opposed to the deferred acceptance, which uses order n bits of communication and preference learning, this only uses order square root n plus some polylog terms that I'm suppressing. And this is near optimal because we can prove that there exists a separable market such that anything that finds stable matching with high probability need omega square root n. So there's only a polylog n gap here. As well, this has good incentive properties. Now, about incentives, there's some inherent limits to anything that finds stable matching. So even the deferred acceptance algorithm is only strategy proof for the proposing side. But for the other side, they can truncate preferences. However, no agent in deferred acceptance can deviate and get someone better than their best partner under any stable matching. And we show that this inherits our protocol inherits this property of DA with high probability. However, there are two limitations. The first one is that it's sequential in nature, so whom I signal depends on who signaled to me and depends on who signaled to them, and there can be a very long chain. As well, we require public messages in the sense that we need firms to be able to, in one go, broadcast this higher qualification requirement to the entire market at unit cost, instead of broadcasting individually to everyone, which will be very expensive. So these two things are hard to get past in a general separable market, but we can overcome them in a more stylized model of preferences, in which both workers and firms are partitioned into tiers, with everyone preferring better tiers to worse tiers. And within each tier, preferences are uniformly random. This is also called block correlated preferences in earlier work. So as in the previous separable market, one key to reducing communication overhead is to give agents a sense of whom they have a chance of getting. And the way we do this is this concept called a target tier, which is intuitively the best person I have a strong position against. So it's the it's the tier on the other side in which their endpoint is just below mine. So for these top workers, they have a strong position against all the firms, but the best firms are these firms. So their target tier is the top firms. And for the top firms, their target tier is the second tier of workers. And then the key idea is that we want to encourage people to focus on their target tier, the best people for which they have good chances with. So there are 2 rounds. In the first round, every agent sends a certain number of signals to their most preferred partner among their target tier that I just defined. And in the second round, people respond to these signals and submit a preference ordering of people whom either signaled to them or whom they signaled. And finally, we just run deferred acceptance to find a stable matching in this subgraph of signals. And you can show that the result of this is stable with respect to the full preferences, not only the subgraph of interactions with high probability. Also, the communication and preference learning costs are low, being only polylog n instead of square root n. There's also good incentive properties as before. And finally, we only require 2 rounds rather than many, many rounds. As well, people only need to know the signals they were involved with. So now let me conclude by commenting on what are some of the insights for real matching markets. So the key we find in this theoretical work about how to reduce communication overhead, there's 2 big ideas. So the first idea is that we want to get people a sense of whom they have a chance with. So ways we see this idea in practice includes, for example, universities maybe publish forecasts to their admission thresholds, which, for example, is done already in some universities in Israel. The second idea is that we want to encourage everyone to focus on reaching out to their favorite people whom they have a chance with and wait for their dream matches whom they have very little chance with to approach them rather than the other way around. So I want to focus for each individual agent, they may have incentives to go after the dream matches. But in the aggregate, if we encourage everyone to do this, then the dream matches will approach them, and it's a good equilibrium. So the way one can think of implementing this is nowadays there's many matching markets that are done online. So these online platforms, to reduce the aggregate search costs of participants, can maybe in showing their list of options, first show these realistic options for these people, because these websites can also estimate based on the data whom you have chances with. So these are just some ideas of how to take insights from this theoretical model to a wider application. But there's a lot of open questions still remaining, even in the theoretical model, like can you do more with the separable markets? How many rounds do you need? As well, there's also questions about if you want to really apply this in a particular market, there's much more richer modeling that needs to be done. So if you are interested in any of this, I really encourage you to come speak to me or my collaborators afterwards, and hopefully can get you excited on working on this as well. And that concludes my talk.